Hello, my name is RJ Harden, and on behalf of my team, I'm presenting the results of our project Learning to Diagnose from Clinical Notes for Georgia Tech's Big Data Analytics for Healthcare class. The objective of this project is to develop an accurate machine learning classification model for a patient's diagnoses using clinical notes alone. The motivation behind this is that currently medical services are provided on a push model. That is, that a patient develops a condition and goes to the hospital and is given a service. But it'd be a lot more efficient if instead we predicted before the patient develops the condition that the condition will arise. We're hindered in doing this because of our inability to make accurate predictions from medical records, many of which are very unstructured. We suspect, our team, that LSTM's long short-term memory models will be able to take advantage of their inherent structure to draw out useful information from clinical notes. To test our hypothesis, we focused our attention on the MIMIC3 dataset, a 3.9 gigabyte medical repository for over 50,000 patient admissions at a large U.S. hospital in Boston. This repository contained not just information about admissions, but all that goes along with it: clinical records, demographics, billing information, laboratory results, and so on. In particular, we focused on the unstructured format and information within the notes table. As an example, on the bottom left, you can see a subsection of the notes. These are written by presumably doctors and other medical professionals in a semi-formatted way. It has a discharge disposition, facility, discharge diagnosis, but this is all contained in a single string. And to be able to draw useful information out of that, you need a model that can separate and pull and extract structure from it. Again, the goal of this project is to see whether LSTMs are a useful tool in making predictions on this unstructured data. Before we can feed information into the LSTM, though, we need to do two things. We need to pre-process the original unstructured text. We did this with the NLTK library by removing stop words, and then using a limitizer, which would take words and reduce them down to their simplest representation. For example, changing verbs with different tenses down to a single tense. We also removed non-alphanumeric characters and extracted out relevant terms, as seen in the last slide, like discharge diagnosis, into a separate feature. We then embedded the output of the preprocessing stage using a word-to-vector model into a numeric representation. The goal of this word-to-vector numeric model is to output numeric forms for different words where the distance between forms is minimized if the meaning is the same. For example, the words apple and pear should have a very small distance, but the words apple and truck should have a larger one. Anyways, the output of this model is a numeric representation which can be fed into the LSTM model. Consider two classifiers in addition to the LSTM model: a random forest and a simple traditional RNN. Our initial expectation is that the LSTM would perform the best, given its robustness to the long-term dependency problem that RNN faces, and its ability to use memory, something that a random forest can't. On the right is a bit of details on how we put together our LSTM, with 3 layers on the bottom: an embedding layer, the LSTM itself, and a dense layer. And then on the top is a diagram of how LSTMs work, using 4 layers within each cell, and then a chain of cells moving across from left to right. We ultimately used 100 hidden units per layer. What did we observe after all of this? We saw a small but consistent accuracy advantage when using an LSTM. On the top right, we have a comparison of the 3 classifiers against both a 400 megabyte subset of the MIMIC database and then the entire dataset itself. We see that random forests do terribly. Just to give context to this number, there are 54 total classes in the MIMIC database for diagnoses. RNN and LSTM are very similar in performance, but LSTM beats on both counts by a percentage to a percentage and a half. On the bottom right, we observe accuracy by epoch. As the number of epochs continues, both the loss that LSTM see is smaller and the accuracy seen is greater. We conclude that LSTMs are more accurate. However, we want to note that the compute time required by LSTMs is significantly longer, and that this accuracy doesn't come for free. I want to close with some thoughts on how further improvement gains could be realized in additional iterations of this project. And also want to thank Professor Sun and the TAs for their help throughout this project and this course. We learned a ton about LSTMs, natural language processing, dealing with large amounts of unstructured data, and we'll take that away in our careers going forward.